Hey, awesome AI explorers, what's happening? Today we're diving deep into a super cool algorithm. It's called K-nearest neighbors, or KNN for short. You're gonna love how simple and powerful this is. KNN is a fundamental tool in machine learning. It helps computers make smart decisions. It's all about finding similarities in your data. Think of it as a digital detective. It looks for clues in nearby data points. This helps it classify new things or predict values. It's incredibly intuitive. So, what does KNN actually do? Imagine you meet someone new. You might try to guess their interests. How? By looking at their friends. If their closest friends love sci-fi movies, chances are they might too. KNN works exactly like that. It looks at the neighbors of a new data point. These neighbors are the existing data points we already know about. Based on these neighbors, KNN makes an educated guess. It's a type of instance-based learning. That means it doesn't build a model beforehand. It just uses the entire dataset for training. This algorithm is super versatile. You can use it for classification tasks, like, is this email spam or not spam? Or does this customer belong to segment A, B, or C? It's also great for regression tasks. This means predicting a continuous value. For example, what will be the price of a house? Or how many likes will a post get? Its simplicity is its strength. It's often one of the first algorithms beginners learn. And for good reason, it provides a solid foundation. KNN is used in tons of real-world applications. Think about recommendation systems. Netflix or Spotify might use something like KNN. They suggest movies or songs you might like. How? Based on users with similar tastes to you, your nearest neighbors in terms of viewing or listening habits. It's also used in image recognition and even in finance for fraud detection, or in healthcare for predicting diseases. It's a true workhorse algorithm, simple yet effective in so many areas. Get ready to master it. Alright, let's get a little mathematical, but don't worry, it's simpler than you think. KNN operates in what we call a feature space. Imagine a big chart. Each data point you have is a dot on this chart. The position of each dot is determined by its features. For example, if we are classifying fruits, one feature could be sweetness, another could be size. So, an apple would be a dot, a banana would be another dot, each with its own sweetness and size coordinates. This chart is our feature space. Now, a new, unknown data point comes along. Let's say it's a mystery fruit. We plot this new fruit onto our feature space, based on its own features, of course. KNN then needs to figure out what this fruit is, or what its properties are. To do this, it looks around. It finds the K closest known data points. These are its nearest neighbors. The K is a number you choose. It could be 3, 5, 7, or any other integer. This K is super important, but more on that later. So how does KNN measure closeness? It uses a distance metric. The most common one is Euclidean distance. Remember Pythagoras from school? It's basically that. The straight line distance between 2 points. If you have 2 points, x1, y1, and x2, y2. The distance is the square root of x2 to x1 squared plus y2, y1 squared. This tells us exactly how far apart two data points are. In our feature space, no matter how many features dimensions we have. The principle remains the same. We calculate this distance. Once KNN finds the K nearest neighbors for our new data point, it then makes a decision. For classification, it takes a majority vote. If K is 5 and 3 of the 5 neighbors are apples, and 2 are oranges, then KNN will classify the new fruit as an apple. Boom, simple democracy. For regression, it usually takes the average. If we are predicting house prices, KNN would average the prices of the K nearest houses, and that average becomes the prediction for the new house. See? The math is just about distance and voting/averaging. Choosing the right K value is crucial. It's a bit of an art and science. If K is too small, say K equals 1. The model can be very sensitive to noise. Imagine one noisy data point being the closest neighbor. Your prediction could be way off. This leads to high variance. The model might fit the training data too well, but it won't generalize well to new, unseen data. We don't want that. We want our model to be robust and make good predictions in the real world. On the other hand, what if K is too large? If you choose a very big K, the model might become too generalized. It might smooth out important local patterns. For example, if K includes almost all data points, then every new point might get the same classification. This is called high bias. The model is too simple. It underfits the data, so we need a balance. Finding the sweet spot for K often involves experimentation. Techniques like cross-validation help us choose an optimal K value. It's all about that bias variance trade-off, folks. Now let's talk about the measuring stick, the distance metric. Euclidean distance is popular. It's the as the crow flies distance. But it's not the only option. There's also Manhattan distance. Imagine navigating a city grid. You can't go through buildings. You have to travel along the streets. Manhattan distance calculates the sum of absolute differences between coordinates. This can be better when features are not directly comparable, or when you have high-dimensional data. Other distance metrics exist too, like Minkowski distance, which is a generalization. Euclidean is Minkowski with p equals 2. Manhattan is Minkowski with p equals 1. There's also Hamming distance for categorical features. Choosing the right metric depends on your data and the problem you're trying to solve. It's important to understand your features. Are they continuous? Are they categorical? Are they on different scales? If features are on different scales, like age and income, you might need to normalize your data first. Otherwise, features with larger values will dominate the distance calculation. Alright coders, let's get practical. Time to write some Python. We'll use the amazing scikit-learn library. It makes implementing KNN super easy. First, you'll need data. Let's say we have a data set of flowers, with features like petal length and petal width, and we want to classify the species. Scikit-learn has built-in datasets like Iris for this, perfect for learning. So step 1, import necessary libraries. For numerical operations, 4 and 4. Next, load your data, separate it into features, X, and target labels, Y. Features are the inputs. Target is what we want to predict. Then, split your data. We need a training set and a testing set. The model learns from the training set. We evaluate its performance on the testing set. This tells us how well it generalizes. Does this beautifully. It shuffles and splits the data for us, keeping things fair and unbiased. This step is super important. Never test on the data you trained on. Now the fun part, create the KNN classifier. Here is our K value. We're starting with 5. Then, train the model. That's it. The training in KNN is just storing the data. It's a lazy learner, remember? Finally, make predictions on your test data. You can then compare these predictions with the actual labels and see how accurate your KNN model is. You can try different K values to find the best one. KNN pops up everywhere. We talked about recommendation engines. It's also an optical character recognition, OCR, helping computers read handwritten text. In bioinformatics for gene expression analysis. Strengths, it's simple to understand and implement. No assumptions about data distribution. Weaknesses, it can be slow for large datasets, because it calculates distances to all training points for each prediction. It's also sensitive to irrelevant features, and the curse of dimensionality can hit hard. But hey, it's a fantastic algorithm to have in your toolkit. Keep learning, keep building.